Hey guys, welcome back to the channel. Today we're going to be covering decision trees. So, what's on the agenda for today? Well, what is a decision tree first of all is what's going to be covered. We're going to cover how decision trees work, the pros and cons, how to improve decision trees, and also we'll be covering feature selection as well. And there'll be a short brief on how you can do some math on decision trees, but we won't be going too much into that detail. Um, so what is a decision tree? A decision tree is a flowchart-like tree, and it's used for classification and regression. It's also known as a CART algorithm, classification and regression tree. Um, Essentially, in a decision tree, it's quite a good algorithm to visualize. It's kind of like when you make decisions on a daily basis and you produce like some sort of diagram that would represent your decisions. So, for example, here, um, I have a decision tree that will help to assess if we should surf or not. So if there is a swell, um, then we can go on to more different questions. For example, wind direction as well. But if it isn't a swell, for example, we won't surf. So in this way, we split on the features that matter to us. So here, the features that matter are swell, high wind, and wind direction. And based on that, we will then assign a predictive model. What I mean by a predictive model is essentially whenever you have like the end of your decision tree in your leaf, it's the outcome that will actually appear from the grouped um, data sets that have been split. So, for example, when we split on, let's say, high wind to low wind, we produce two different data sets. So we'll have a data set where we only have um, sort of features, well, not features, sorry, but records of data or instances of data where we have high wind, and on the other hand, you'll have instances of data where we have low to no wind. So that's essentially what a predictive model is, which is our final outcome. So how does it work? Well, first we start with the full data set and we consider all the splits. Now, the way we split in decision trees is based upon reducing the amount of uncertainty within the data with respect to our classes. Because the whole point of either classification or regression is to be able to predict something, right? We want to predict something. And so by reducing the number of, by reducing the uncertainty we have, we're more likely to predict. And in order to reduce the uncertainty, we must increase the amount of information we have so that we can make a more informed decision, right? So in order to do this, we have a purity metric. So usually it's either entropy or Gini's metric. Entropy is the negative sum of the probability times by the log of the probability for a specific class. And um, this sum is all over all of these sort of classes. Um, and Gini's impurity is defined as 1 minus the sum of the probability of the class squared. You should be able to find these on Google or on the slides, so I haven't included it for today in this presentation. So when we have this impurity reduction, we want to select the best feature to split on that will reduce the sort of entropy or this Gini's impurity the most. This is also known as information gain. It will lead to a reduction in uncertainty so that our new groups have less entropy. So this means that the probability of the machine learning task, i.e. classification or regression, will become more certain. We then um, sort of have this image of like a node at the top being our data set, and we split it into two data sets depending on the best feature, right? So when we split on the best feature, we will continue to do this on the child nodes that we produce. So let's say splitting on like high wind and low wind, we would then do the same sort of entropy mechanic that we did and do this and continue until we reach a stopping condition. Now, this stopping condition is usually the max depth, or where there's no further impurity reduction. Um, so when you think about a decision tree and like let's say the features and whatever, the you could be splitting like for ages and ages. Given you have like an infinite amount of features, you could be splitting for however knows, you know. So decision tree splitting can actually become such a big thing. Your tree can have such a massive depth. And controlling the depth of the decision tree is one of the main things that will affect how good your decision tree is. If you only split, for example, on one feature, you're not really going to gain much information to make good, robust predictions for a model, right? But at the same time, if you split too much, you're basically going to overfit your model. You're going to overfit your data. And at that point, you'll find it really, really hard to generalize on new data, right? So we um, want to be able to find a good stopping condition in our decision tree. And then once we stop at this stopping condition, we will then assign a predictive model, which is what we'll move on to next. So the predictive model is it usually depends on the machine learning task that you perform. So there's obviously two different types for decision trees, classification or regression. When it comes to classification, it's usually a majority vote or something similar. Um, so let's say we wanted to classify, um, hmm, let's say we wanted to classify if a person has a disease or not. We would have a decision tree that would split upon features related to the disease, and we would look at the instances left within the data once we've gone through all our decisions. So we basically traverse down this decision tree to the leaf, and then at the leaf where we have this predictive model, we will look at all the remaining instances of our data, which are obviously going to be labeled, since this is a supervised learning algorithm, and we will just do an average vote based on that remaining data. We can also do regression. So let's say we wanted to predict the probability of something. We could do that with decision trees by applying some model on the data set. We could do that for probabilities, obviously, it's going to be more so logistic regression than linear regression. But obviously, for other machine learning tasks, you can use linear regression. Now, decision trees are quite good. Um, as we saw in the previous few slides, we have good, easy to interpret and visualize sort of trees that we can use, which makes it easier for us to actually find better parameters for training. They handle large data sets with high dimensionality as they split on the features. It works great with obviously classification and regression. It's an algorithm that can do both. It works with numerical data and categorical data, so we don't really need to have that much data pre-processing, so it's good um, in the real world, when actually making your machine learning models is quite an easy, quick thing to do. And it also allows for non-linear patterns to be analyzed. If you think about things like logistic regression and linear regression, um, more likely than not, it's going to be linear, right? But obviously, that's not going to be working on quite a lot of different um, problems, right? Not everything is linear. So then what are the problems about decision trees? Why is it bad? So firstly, it doesn't allow for extrapolation. So back to A-level maths, if you guys have done it, um, linear regression, you could always plot like a y is equal to mc graph and extrapolate and predict, right? Um, but basically, when you have a lack of data within decision trees, it's going to be harder for you to extrapolate on your data. It doesn't really support that. Um, Another thing that's bad about decision trees is that it's sensitive to small changes in data. It's sensitive to noise. For larger data sets, it's quite expensive to do training on it. Um, like I was saying before, the optimal decision tree or the maximum decision tree, it's NP complete. So obviously NP complete problems, um, I believe it's that they are exponential in order to verify the solution. Please do correct me if I'm wrong. Um, okay, I realize I have Q for quiet. That's just from the slide template. So apologies for that. Um, but also decision trees are biased towards classes that dominate in data. So if you have a really biased data set, your decision tree will most likely learn that bias. And if it learns that bias, obviously it's not going to be a really good model predictor. It's not going to be good at predicting things for whatever machine learning task you're doing. And finally, like we said before, it can overfit. So it requires sort of like dependencies in some cases to prevent this overfitting. And one of these is pruning. So improvements, how can we actually improve our decision tree? So first of all, we can ensure a maximum depth to not go to a full depth tree that is usually complex and overfits. So by limiting how sort of deep our decision tree goes, we can prevent the complexity of the model from going too complex and hence prevent overfitting, which allows us to then generalize on new data. As it said on the previous slide, we can prune the tree. Now, pruning is basically just a technique when we have a high depth tree. All we do is we remove low importance splits. So we'll go to nodes and find how important they are, and we'll just remove the ones that are not as important. Um, we can also do feature selection by picking the top K features. So this will obviously also drastically reduce the number of splits we do because we actually split on the features. And we can also apply ensemble methods, which are basically just methods that will use several models together, as the name suggests, an ensemble of methods, um, like bagging, to improve model robustness. How do you measure importance? Uh, Importance is measured by quite a few things. So obviously, when we talk about feature importance, when we actually do a decision tree, we have things like entropy, we have things like Guinea's impurity, which tell us about how uncertain we are, how little information we have about making a prediction based on the current information, right? And it tells us a little bit about the variance. So basically, anything that relates to information is going to be some feature of importance. So if we have a high information gain, it's more likely to be an important feature for our model. Exactly. And also ensuring a maximum number of leaves um, is basically just limiting the number of leaves that we have. So this can also directly influence the depth because obviously, let's say when you do BFS, right, or DFS, if you have less um, if you have less leaves, that's obviously going to influence your depth. Your depth is logarithmic with respect to the number of nodes you have, and the leaves is the cumulative number of nodes with respect to how many levels you have. So you can obviously see that difference there. And also just doing basic model stuff that you would usually do with any machine learning task, such as cross-validating. To instead of just using a train test split, you can actually find the best parameters for your tree by doing something like k-fold cross-validation um, with various different decision tree parameters. And there's also a thing that's called grid search. This isn't examinable, but I'll talk about it because it's quite cool. It's basically like a brute force search for your decision tree to find the best parameters that will find the best accuracy for your model um, as well. It's pretty cool, um, but obviously not an examinable thing. So we talked about how to improve decision trees. One of the ways that I mentioned was feature selection. How can we actually do feature selection? So firstly, we find the maximum mutual information feature and we add it to an empty subset S. So this is just a notation S for now. It's just a subset of the features that we want to select, right? So mutual information, as we were talking about before, is going to be something that's more important. So higher mutual information between the feature and the output. So this is what we actually want to find. We want to find how much information the output and our feature shares. Because if our output shares a lot of information with our feature, then that means that our feature is going to be really good at helping us to predict our output, which is obviously the whole point of our machine learning task. Another thing as well is then going to be repeating it, but we don't want to consider the redundant information. Like let's say we have 5 features and 3 of them tell us the same thing about why. Why should we have duplicates? Why should we have to process more features within our decision tree if it tells us the same thing, right? So in this way, we're implementing a greedy feature selection algorithm that will maximize the mutual information between the features that we select and the output, but also minimizing the mutual information between the current subset of features that we've selected. And that just means that we're not considering that redundancy anymore. We are not allowing for duplicate information to be selected. Um, and then self-explanatory, we just repeat until we have k features. Now, there are algorithms that will actually help you to select a good k. Um, these are more so dimensionality reduction algorithms, such as like PCA, things like that. Obviously, you don't need to know this for the exam, but I think it's still worth having a look on how you can actually um, select K features, just so you can get a better idea of machine learning and decision trees. But yeah, mutual information is also information gain, and information gain is a measure of importance as well as mutual information. We have the equation here on this on this screenshot of the slides. Um, so it's equal to the entropy of x minus the entropy of x given y. Now here there isn't a particular meaning to x and y, but we can assign it one. So when, let's say x is one feature and y is our output, if the mutual information between the two, if our information gain is high, that means that x tells us a lot about y and vice versa. So yeah, in that way, by maximizing mutual information, you can improve the you can improve your splits, you can improve feature selection, and hence get a better model. I won't be covering any maths today, but if you have a look at week four's exercise sheet, try it out and look at the mark scheme once you've tried it out. This is a good idea. I have also posted my own exercise sheet for as well in the recaps, which you can just scroll up in the recaps if you're interested. But yeah, no, that's basically it. Decision trees is quite a simple topic. Um, yeah, cool. So thank you guys for watching. Make sure to like, subscribe, comment down below, and ping up the notification bell to watch more videos like this.